Bismillahirrahmanirrahim. Hello friends. In this video series, we are going to explore the design of different types of solar supporting steel structures using STAAD.Pro, one of the most widely used tools among structural engineers. But what makes this series a must watch? Because we are not just using STAAD, we are unlocking its true potential with the STAAD editor, a powerful yet underrated feature. On top of that, I have developed a smart Excel sheet powered by VBA macros that does not just calculate dead and wind loads for your solar panel array, but it transfers those loads directly into STAAD within a single click. We will also dive deep into steel design parameters and how to interpret them correctly within the software. To start off, we'll be working on a 2x1 solar array in landscape mode. So let's jump right into the software and begin.
Before getting started, if you are new to our channel, then please hit like and subscribe button and share as well with your friends. And let's learn structural engineering together. One more thing, we have already started design courses related to reinforced concrete structures and steel structures along with the steel connection design. If you did not watch those videos, then please go and watch those. Links of these videos I am sharing in the description below. So let's get started.
So we are here in AutoCAD software. So we are designing the solar array of 2x1 in. So we will be first making the solar panel array layout, actually a plan view of the solar panels arrangement, and then we will going towards the section of that particular structure, and we will be model in our software STAAD.Pro. So let's start. This is the data sheet of the solar panel in which some required parameters will be given here, like the panel dimensions, which is 1134 by 2278 and 1400 mm or 1200 mm or 790 mm or 400 mm. There are four different mounting holes center to center distances, but we will be using the greatest one, which is 1400, so that our panel cantilever span will be less. The weight also mentioned here, 31.8 kilograms. This is our requirement with respect to our structural design of the structure. So let's go towards the AutoCAD. Since we are modeling 2x1 in landscape mode, 1134 dimension will be parallel to slope direction. So modeling the plan view in the AutoCAD, this is the projected one. So we need to have the projected dimension. So 1134, and the angle of tilt will be using 25 degrees. So 1028 will be the planned dimension of the panel. So let's draw a rectangle of 2278 by 1028. Let's change the color from cyan to green. Now let's just copy this and paste it just after the other solar panel. Physically there will be some gap between these two panels, but here for structural modeling purpose, ignore that one for simplification. Now let's draw the construction line at the center of the panel, and we are having the 1400 mm center to center distance, to offset of 700, 1400 half, 700 left and 700 right, and then trim. Alright, now since the length of the panel is 2278, so we will be projecting the beams 50 mm both sides. So 2278 plus 50 plus 50 means 2378. So let's draw a rectangle of 2378 by 100. So this is because the single line will be overlap with the intersection of the two panel lines. So that is why I am drawing a rectangle here to indicate the position of the beam. Alright, so this is a beam. These are the two purlins, and now making a column as a rectangle, but actually there will be a pipe column, pipe section. So 200 by 200, and let's just move it towards the center. Alright, now let's draw the horizontal line as a base of the structure, means the bottom of the column, and we are required a clear height above the, and we are required a clear height under the structure is 2100. So let's just offset 2100 line, which is this, and then make this as a block, and let's just copy this and paste this. Now make a line of whatever length but inclined at 25 degrees. Align this structure array with this line towards the smaller dimension as we have discussed. So from this center to this one, this is the column, and create the line here to here and remove this array. So this will be our section of the structure. Why we need this? Because for the modeling purpose, this particular height is actually 2100, and we need this total height to model the column in our structure software, so which is 2534, right? So let's go towards the STAAD.Pro. Go to the geometry and turn off the grids. Make sure to have the unit of Newton and millimeters, and let's just create the first node 0, 0, 0. Now select the node cursor, select the node, Control C and Control V. In the Y we are having 2534, so this will be the starting and ending node of the column. Now we will be having this inclined beam, so just identifying its horizontal and vertical component, which is 932, 434. 932, 434. Copy 932. 932 in the negative x direction, so 932, and in vertical also negative 434. Similarly, positive 932 and positive 434. Alright, now connect this with the beam. For all the beams, down to up, down to up, and for columns, down to up. Columns up to you, but beams down to up for simpler load assignment from the sheet. Okay. Now going towards the plan of the structure, here is the total beam, which is having the total length of 2378. So we are having the half of this 1189. But now from center to this purlin, this is 700, and then from this purlin to end of the beam is 489. So 700 and 489. So let's select this beam, Control C, Control V, and in Z direction minus 700, and in Z direction again plus 700. Now this particular point will be in minus 489. Yes, and this particular will be plus 489 in Z direction. Right? Yes. Now connect them. And there is no beam here. Alright? Why? Because in the plan there is no beam here. Only the purlins are here and here. And this is the main beam. So we have modeled it. Okay? Now if we leave this beam as it is, so it will be acting as a balanced cantilever. Right? But we will not do that. Why? Because in this way, the size of the beam will be much greater. So to reduce the size of the beam or to optimize design, we will be having the simply supported beam by using the bracings. So let's measure the total distance, which is 1189. So 1189, and we will be having the bracing angle such that it will be lies between 30 degrees to 60 degrees. If it is closer to 45 degrees, that will be very much effective. So let's keep it as a 45 degree. So let's select this one, and in Y, let's say 1189, the same distance as we are having in the horizontal dimension. So connect this and connect this. So this is the structure. Alright. Now the clear height under the structure with the up to the brace is actually 1345 millimeters, which is actually 4.5 foot. Alright. Okay. Now this is the structure, and now we will be going towards the section definition. Go to the general tab, go towards the section database. We will be using W section for the beams initially. Let's say we will be using the least size 4 by 13, then we will be using 5 by 16, 5 by 19, and let's just enough. We will be start our trial by the least weight. W4 by 13 means depth, because it is an American section. So the American nomenclature, the first number is the depth of the section and the second number is the weight of the section. So this is actually in the inches, these names. So 13 means 13 pound per foot. Right? Now for column, we will be using the pipe. And so for the column section, we will be using pipe. And for the brace, also we will be using pipe section. And for the purlins, we will be using the channel section. So pipe, we will be starting with the least size, which is we will be starting with the size of 1 inch. So where is the 1 inch? Actually, this is a standard of 3 inch, 2.5. This is 1 inch, and this is 1.5, 1.25, 1.5, and 2 inch, 2.5, 3 inch, 3.5, 4 inch, and 5 inch. Now channel section, we will be using the least size 3 by 3, 3 by 4, 3 by 5, 3 by 6. Okay, so these are the sections. Now let's just select this and assign this. Now for the beam section, W4 by 13, so use cursor to assign this, this. And for the pipe section, we will be start off with the 3 inch. For the column section, 1 inch for the bracings. Right? Now when we click the 3D rendered view, so this is our structure model, but here we can see that this particular beam, blue beam, must be inclined with the same inclination as the tilt angle of our structure, of the solar panels actually. So to do so using the beta angle, create beta angle, which is actually 25 degrees. Okay, and use cursor to assign beta angle, beta angle, beta angle. Alright, now checking the rendered view. So now the blue beam, which is actually the main beam, is at the inclined orientation. Going towards the specification tab, we will be assigning the beam release command, beam releases, to these braces, as they are not capturing the bending moments at their ends. So go towards the beam button and start. Actually, the cross-sectional axes, local axes are MY and MZ. So start MY, MZ again, and MY and MZ. So just start, use cursor to assign this, and for the end also. Okay, so beam release have been assigned. I think that this is not assigned. Okay, now the beam release has been assigned to both our braces. Now further beam releases are not required, as the beam is continuous over the column and the purlin are also continuous over the beam. Okay, now going towards the support tab, create one fixed, add, create support, use cursor to assign, and assign this as a fixed support at the base of the structure. Now save our model. Okay, now we will be going towards the load definition. Here we can see that the load case detail, the second one, is actually empty here because we are not created any load cases or load patterns. So to do this, we will be using a smart sheet, which is actually an Excel sheet. In that sheet, there will be load calculation for dead load of the solar panel, load calculation for the wind load of the solar panel, and not only the calculated one. And then that sheet is able to transfer those calculated loads to the corresponding softwares by using some algorithm. And I have developed that sheet by using VBA macros, which is actually a programming language. Going towards that sheet, so go towards the dead load tab and just plug in the weight of the panel, the single one, which is 31.8. Number of panels in total array is 2. Right? So there is a total weight in kg, there is a total weight in kilonewtons, and there is a total weight in the corresponding nodes, interior and exterior one. Now the wind loads. Wind loads tab. The first one is the wind speed. So we will be having the wind speed of, let's say, 175 kph. Alright, this is in mph and this is in meter per second. The wind exposure is exposure C, as we are having the open terrain. Our site is in the open terrain. Now, the mean height of the solar panel. As we are having a single column, so just the total height, which is 2534. So here the unit is meters, so 2.534. Right now, in the direction of slope, panel dimensions, solar panel arrangement, panel dimensions, in the direction of slope. So in the direction of slope, actual dimension. So in the direction of slope, this is 1134, and across it is 2278. So 1134 and other dimension is 2278. Now rows parallel to slope. So this is our slope direction. Right? So how many rows in the slope direction? 1 and 2. Right? And how many rows in the other direction? Only 1. Okay. So rows parallel to slope is 2 and row in other direction is 1. Number of minus panels, leave it as 0 because we are not having any minus panels or reduced panels. Now all the loads, wind loads have been calculated automatically. Dead load as well, towards with the help of this sheet. Now going towards the wind coefficients. As we are having the 25-degree tilt, so we will be plugging 25 here, but we will be using the approach of monoslope open structure. So there are some coefficients CNW and CNL with respect to roof angle and with respect to load case, clear wind flow and obstructed wind flow. If you want to learn more about the theoretical concept of this solar panel wind load calculations, I have mentioned all these concepts in a video, and I am giving the link of that video in my description below. So first check out this, and so that you can confidently use this sheet. So there is a table in which there are some roof angles: 0 degree, 7.5, 15, 22.5, 30, 37.5 and 45. But our desired value is not there. So we will need the use of interpolation. This is the interpolated angle. Just plug in 25 here, and 25 is in between of 22.5 and 30. So let's plug in 22.5 in the upper and 30 in the lower. So these are the coefficients that have been interpolated, and automatically the wind loads calculated like this one. Okay. Now going towards the frame loads for STAAD. Now this particular sheet, there is a button of help in which I have mentioned all the nomenclatures used in that sheet to produce efficient algorithm STAAD editor script for automatic transfer the loads. Okay, so we need to just understand it. So there is on the left side, there are the two pictures. On the left side, loads joint type details when even number of panels along the slope, and in the right side, loads joint type details when odd number of the panels along the slope. So we are having 2 panels in the slope direction, so we will be using the even number, the left one. Okay, so we will be starting our numbering or our load application from the bottom one, from the lower side, So there are 4 panels drawn in their picture typically, and there is a central line passes through the array of these center of this solar array. There are 2 purple lines. One is the upper one and the lower. The lower one is called the reference beam line, and the upper one is actually only the beam line. And the green line is actually the purlin. The magenta or purple line are the main beams. Dashed line are the center line along the slope, and interior load points are the red one, and exterior load points are the blue one. What is interior and exterior? You have to watch that video, which is actually giving all the concepts related to wind loadings on the solar panels, dead and wind loadings. Okay, so there is a upper region, there is a lower region. There are 3 segments of the purlin. One segment is below the reference line, one segment is above the upper magenta line, and one segment is in between these 2 magenta lines. So lower one is segment 1, middle one is segment 2, and upper one is segment 3. So now for segment 1 and segment 3, there will be generally there will be only exterior points, okay, loaded. In the segment 1, the exterior point is at the start of the purlin, and segment 3 is the exterior load point at the end of the purlin, usually end of the purlin, approximately. And in the segment 2, there are 3 interior points, which is actually the combination of 2 purlins, means combining these 2 points, and it is actually very close to each other. So we will be assuming that these are the interior one, which is actually having the double loads. So these are the 3 points in the segment number 2, which is distant from the reference line as point number 1 A, point number 2 B, and point number 3 C. So all these distances are referenced from the reference line, which is actually the main beam, because in the softwares, each and every beam element or line element must be intersected altogether. Otherwise, the load transfer mechanism will not be properly done, and errors may occur. So the segment 1 it is actually at the lower region. Exterior point in the segment 1 is called L1. In segment 3, exterior point is in the upper region, and it is called U1. So by reading the definition, U1 is actually exterior load point on the upper region at the end of the segment 3, and L1 is the exterior point on the lower region at the start of the segment 1. Now, what is U2, L2 and UL? UL is actually in between. UL is actually on the center line. Okay, so half load will become from the upper region and half load will become from the lower region. So make it U and L, UL. Okay, now U2 means upper region double load, L2 means lower region double load, L1 means lower region single load, U1 means lower region, U1 means upper region single load. Single load always be on the exterior load and its exterior load point, and double load always will be on the interior load points. A, B, C are the dimensions of the interior load points from the reference line. L1 to be approximately at the start of segment 1. Approximately. Actually, we are projecting the purlin some length greater outwards the edge of the solar panel to clamp it or other safety purpose. Alright. And similarly for if we are having the odd numbers, so there is some difference, which is the center line now is actually passing through the center of the middle solar panel. So there is no UL point. The rest is the same. Okay. So let's go back towards our sheet. So by using this sheet, we will be actually making an algorithm script of the STAAD editor and just paste it in the STAAD editor, and all the loads will be automatically transferred. Now in STAAD, just select the purlins, view selection objects, shift B to view the beam numbers, and shift K to view the nodes. Now 4 and 6, there are 4 beams, 4, 6, 5, 7. So in this layout, we are making the numbering same as the STAAD 4, 5, 6, 7. These are the purlins. Okay, so this is the load point, this is the load point, and this is the load point. So this middle one is actually the center load point, and these are the exterior one. So here only one interior point, which is at the intersection of these two solar panels. So only UL, and this one is L1, and this one is U1. Okay, so for beam number 4, load joint type is actually L1. Intermediate distance is 0. Local axis of beam for wind. Press Shift O. So this will come, and the red arrow shows y-axis, green arrow shows z-axis, and blue arrow shows x-axis. Local. I'm talking about local axis. Local y-axis is actually the wind axis, and all the red arrows are upward. Local y, upward. Up means positive +1, and down means -1. So it is +1. Now for beam number 6, again same. Okay, it is up to you now to handle this UL with beam number 4 or beam number 5. For beam number 4, it is the point on the end of the beam number 4, and for beam number 5, it is the point on the start of the beam 5. So I am plug-in as end of beam number 4 and 6 correspondingly. So again, copy this UL, and the distance is end. So beam length we don't know, so just measure this 1028. So just plug in 1028. Okay, now for beam number 5 and beam number 7, same, but in U1 and U1. Remember, don't overwrite these red highlighted cells, as these are the formulas. So now we since we required the beam lengths as well, so STAAD beam length, go towards the STAAD beam length tab, and go towards the STAAD model geometry tab. This structure one beams table, click on this beam heading. So all the table is highlighted as black except this beam button. So just copy, Control C, go to the sheet, place the cursor on the black cell which is A2, and Control V. Okay, so we can see that the lengths are actually here 1030. The STAAD is actually giving the length in the whole number. Okay, now convert data to STAAD editor load. So just click this button and hang on a second. So the message appears, loads data copied. All loads are copied on clipboard. Please paste them into STAAD editor file. So these data is being copied here. Now go to the STAAD editor, search for the end define material, and paste over here, backspace, save, close, and okay. Press Shift O to toggle off the local axis view. Now go towards the general tab, loads and definition tab. Now see, these are the load cases automatically developed. All the loads automatically transfer from the calculation sheet to the software in a single click. But here, one mistake we have done, we have actually set the unit of the input unit as Newton. So all these loads are having the unit of Newton, which is actually the mistake. So let's just copy this unit and paste it here, kilonewton. And we can see that now kilonewton has been written here. As in the STAAD editor, if we use this unit command, so under the unit command, all the commands are being input as these units unless any other unit command comes. For example, here the first unit command, which is unit MMS, millimeters and Newton. So the joint coordinates are in millimeters. Definition material start, E value is in Newton millimeter. Ozone ratio is actually unitless. Density is in Newton millimeter. Alpha is actually the unitless command. Temp is actually the unitless command. Okay, the strength is actually in Newton millimeters. End of definition, material definition. Now there is a second unit command, which is unit MMS and kilonewton. Now under this, all these are in kilonewton and millimeters. Now go towards the command, analyze, perform analysis, no print. Now let's check again. So there will be one error again. which is saying in line 77, 13, 14 and MYMZ. Okay, so let's go towards the STAAD editor file. Member release. So member release command first must come before the support reactions, support condition. Okay, Control S. Now Control F5. 0 error, 0 warning and 0 node. Okay, so the model is working perfectly. Go towards the post-processing mode and let's see the deflected shape under the dead load. Click on animation, deflection, apply. This is the animation for the dead load. This is for the wind load, 0A, 0B, 180A and 180B. There are two things that we have missed here. One thing is that in the sheet, we have missed the distance for U1 1028 as well. So we need to clear all the data first and again run this code. Go to the STAAD editor file and just remove the loads, all the loads here to here and paste it again. Now check all at the 3 locations. For each purlin, the loads are transferred now. And the second thing is that this sheet is not generating the self weight command, so we will be doing it manually by clicking add under the dead load, self weight -1 in Y, add. Self weight assign to view, assign yes. Okay, now we will be proceed towards the design check of these members. First we need to generate load combinations. I have already generated load combinations using AISC 7-05 because we are designing these members using the old code. So just copy the load combinations, strength load combinations and paste it under the last loads value and then okay, the 101, 102, 103 and so on so to 109. Okay, so these are the load combinations. Now one more thing, we need to tell the software to check load list 101 to 109. Alright, now go towards the design tab, just click on the define parameters. CB, we will be required CV, we will be designing the beam members considering flexural members considering CV value of 1 as a conservative approach and FU 0.414 kN per mm square, FY 0.248 kN per mm square and KY and KZ. Since for the column we are specifying K value of 2.1 as for the cantilever column. So KY 2.1 and KZ 2.1 and for LY for the column we will be having 2534 the complete length. KY and KZ and LY and LZ are the parameters to calculate the KL over R slenderness ratio for the compression members. So compression members are what? Columns, bracings, beams which are primarily a flexural member, but in some special cases some beams are having considerable axial member, so it is also designed as a beam column member. So first thing first, the primary slender member could be column, braces. Alright, so KY, KZ and LY and LZ are those parameters which are useful to tell the software to calculate KL over R ratio, and based on that KL over R slenderness ratio, certain calculations are performed. Now LY and LZ, why the software cannot take it as the model geometry? Because for example in our situation there is physical on site, there is a physical column, single column, but in our model we are having the column as 2 segments, 3 and 12. So to tell the software that 3 and 12 are a single entity, so take the total length of 2534 for 3 and 12, both the members. Alright, so that is why LY and LZ are used. But for the bracing, I am not defining any parameter, so it will take the complete length as LY and LZ and calculate it. Because here it is written default is a selected beam's length. If you are not assigning or defining those lengths, then the default length will be considered as the total length. Main 200, yes. Method LRFD, yes. Track 2 for detailed calculations, UNB and UNT. So UNB and UNT are the lateral torsional parameter, lateral torsional length parameter, LB. Since for the flange sections there are 2 flanges, top and bottom, So if any torsional restraint is providing with the top flange at some discrete spacing, so put that spacing for top flange or bottom flange respectively. Since we are having our beam continuous over the column, so it is not having any torsional restraint, so complete length will be considered as UNB and UNT. Similarly for the purlins, because the purlins are continuous over the beams, so the total length of the purlin is considered as UNB and UNT. So what is the total length of the purlin? It is 2056, and what is the total length of beam is 2378. So just go towards the defined parameters. UNB 2056, UNT also 2056. Now UNB 2378, UNT also 2378. Add, okay. And any parameter left? No. Okay. Now go to the commands, check code, add. Now it's time to assign those parameters for the respective members, because there is a question mark display with these parameters. CB I am requiring for all. FU for all, just copy paste the beam numbers here. KY and KZ. KY for 3 and 12. KZ also for 3 and 12. LY and LZ for 3 and 12, for 3 and 12. Right? Main for 3 and 12. Further for 13 and 14. Track 2 for all. UNB 2056 for purlins. So 4, 5, 6, 7. Copy, assign. UNT, copy, assign. For beam 8, 9, 10, 11. 8 to 11. We can also write it. Right? Now check code for all. Now control F5. Save. One warning. A load list command within the load ignored. Load list command, I think, must be after the perform analysis. Now the warning has been vanished. Now go towards the post-processing mode. Beam unity check, and we can see that column is failing, lower column is failing 1.48 ratio, and the rest is past the design. So why is it so? Because to know, just see the STAAD output file. So lower column is actually member number 3. So 3 here. The load combination governing is 104. Failing H1-B. So what is H1-B? It is actually beam column. Yes, it's beam column equation. So here in the check for yielding, there is a major moment. 1.49 exponential 4 means 1490, and the capacity is 1070 only. So here is a ratio of 1.4. Okay. And for the compression, the ratio is 0.169. So add up will be getting here is 1.48 cumulatively interaction. Okay. So flexural compression means when the bending moments of both the local directions and compression component is being interacted with each other, then the ratio is 1.475, and for the tension force, axial tension in the bending moments, 1.41 ratio. Means that the 3-inch column is not past the design. So we need to change it to 4-inch. So let's try first 3.5. So go to section database. If we are not assigning these sections to any beam property, then it will be vanished. That like here we call many of the sections from the section database, but it has vanished because we did not assign all those. So for pipe, I think it's pipe S3.5, right? So pipe 3.5 assigned to 3. Yes. Okay. Now go Control F5. Process. Beam. Unity check. Now it's 1.05, means it is again considered as a failure. So go towards section, database, pipe, and selecting the 4-inch pipe. Control F5, save, post-processing mode, beam, unity check. Now it is passed. Okay, so in this way the solar panel can be designed. So this is up for today. See you in the next video.